Good day and welcome to today's webcast, a part of Electronic Design's 5G Bootcamp. Our topic today, tackling 5G test challenges, sponsored by Anritsu. I'm Bill Wong, Senior Content Director for Conformance Design, Engineering, and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available within the next week. Now let me introduce you to today's speaker. Keivan Isami has spent over 10 years of his career in the wireless industry. As a business development manager for Anritsu, he leads expansion into new market segments and helps guide the strategic direction for Anritsu's family of wireless products. You can find more about our speaker by clicking on the speaker bio widget in your console toolbar. Now let me turn things over to our presenter. Keivan, the floor is yours.
Thank you, Bill. All right, so with no more delays, let's just get started. Today, I am going to talk about tackling 5G test challenges. Let's get started over here. Okay, so what we're going to talk about today is I will give a very quick overview of commercial status of the ecosystem of 5G. Then we'll talk about the test challenges of 5G and the solutions that can address those. So to see where exactly are the commercial networks around the world today, according to the Global Mobile Suppliers Association, GSA, as of October, there is quite a bit of 5G networks available. In Americas, there's somewhere around 5 networks live today. Some of them you may have heard of, like Verizon Wireless, T-Mobile, AT&T, Sprint. But this trend is pretty much all across the world. We have around 14 different live networks, live 5G networks in Middle East and Africa. There's roughly around 20 networks in Europe and 7 in Asia Pacific region. So 5G is here, it's available now, and there are live networks out there. So to put a little bit of terminology in place, as we may be using them a little bit later, there are different use cases and different areas that the 5G network infrastructure is being planned for. At one end, we have what we call the enhanced mobile broadband. In short, we call it EMBB. This is the live streaming, the high throughput, high bandwidth video games, enterprise solutions. It's just the enhanced mobile service that we are used to today. Another use case area is what we call the ultra reliable and low latency communications, URLLC. This is where latency is very important, and the goal is to have a network that responds within 1 millisecond. Applications are anything that you can think of, like driverless cars, mission critical, safety critical kind of applications where latency is important. And the third area is what we call massive machine type communications. In short, we call it MMTC. Here, it's about the total number of devices that are connected to the network. And one of the goals is to have close to 1 million devices per square kilometer of area. With that in place, let's take a look at where the devices are today in the ecosystem. Again, looking at GSA as of October or mid-October of this year, there are over 170 announced 5G devices in the market globally. 38 of them are commercially available today. The rest of them are not commercially available, but they are planned and announced. There are quite a bit of different form factors to these devices. It starts from your cell phones, your smartphones. We have modules, we have hotspots, we have snap-on dongles and adapters, and robots and routers and drones and TVs, all of which are using the 5G device, the 5G technology. The point here is that the 5G is here today. It's happening now. So a quick look at the development timeline of 5G. Up to, if you look at 3GPP, up to release 14, everything is in LTE. Release 15 is when what we call the initial 5G release. Also, we call it phase 1 of 5G. This is where the first standardized 5G release comes out. It's obviously very much dependent on LTE. A lot of dual operation going between 4G and 5G, what we call non-standalone modes, and we'll get to it a little bit later. And there are other releases planned as of now. Release 16 is being worked on. Release 17, other features of release 17 are being looked at release 17. The point is that even though the first version of the 5G is today here, and that's just the core aspects that it was completed in 2017. It was released during this year. But major portions will not be complete basically until next year. Okay, so that being said, let's jump into actual challenges of testing a device. There's been a couple different changes we just talked about. There is millimeter wave and there is under 6 gigahertz frequency bands that 5G supports. There is a variety of bandwidth, signal bandwidths, and carrier spacing and sub-carrier spacing that the UE, the user equipment phone, need to support. As I mentioned, the first release of 5G, the devices support both LTE, 4G, and 5G new radio. So 5G and our 5G new radio is something that's being supported, and there is a lot of dependency and use from phase array antennas. So that's another thing that's being used over here. So because of all of this, it means that the device supports multiple frequency bands. The device has to support at least 2 different radio access technologies. There is, because there's different technologies in there, there is different transmitter chains. It will have to support beamforming, and last but not least, there is typically no RF test port for a 5G device. So what is that? If you look at the challenges that are introduced by including millimeter wave support in the device, is if you look at 4G, the transceiver and antenna could be separately evaluated. What it means is that if you take, you could actually physically connect the cable after the RFIC port and go and test and evaluate the entire transceiver, except for the antenna. The antenna then is evaluated and tested over the air. But in 5G, because of the introduction of the high frequency, because of the introduction of massive MIMO features, transceiver and antenna are very tightly integrated and designed together. So it's not easy to evaluate. The entire evaluation now has to happen over the air. Okay, so what does it mean to us? So two different frequency ranges in 5G operation. We call them frequency range 1, which is under 6 gigahertz. You'll hear another acronym for it as sub 6 gigahertz. And then we have frequency range 2, which is over 24 gigahertz, and it's also called the millimeter wave support. So the typical test system for these two is going to be fundamentally different. The frequency range 1 could be tested in a conducted operation, as you can see on the left side of this picture. So you take basically a base station simulator and connect it to the phone through an RF cable. On the other hand, for the frequency range 2, we need the over-the-air environment. So instead of connecting the phone to the test equipment to a cable, we are using an OTA chamber and putting the phone inside the chamber to do the testing. Okay, so talk about some of the 5G test requirements. So we spoke so far about millimeter wave. What it means is that there is need to establish an OTA test environment. There is a need to measure beamforming performance. There is a need to evaluate new measurements uncertainty and deal with longer test times. This we'll get into it shortly. On top of that, we have a combination of frequency and network architecture in the design of 5G that actually makes the test configurations more complex and more time consuming. We'll talk about this in a little bit as well. And we'll talk about new demands on throughput, on power consumption, on heat dissipation on the device, and simply just the complexity of the conformance specifications. Okay, so let's look at the challenges we have in testing the RF side of the 5G. So the typical things we look at is on the RF performance test cases, such as the frequency, the power, the EVM, spurious emissions. So the dynamic range has changed now. There is requirements on the amplitude phase flatness of the signal analyzer that you have to use. We have to look at the loss budget of the OTA test system. There is the challenges in antenna calibration. You know, you have to look at directivity, the beam width, and phase gain calibration. The speed of test itself is very important now. Some of the over-the-air measurements could take longer, so looking at how you can do that faster is important. The cost of the test system, very important. There is a lot more projects going on now. There is the pre-5G, which I will call like the 5G deployments before the 3GPP. There is the 3GPP 5Gs, and then there's different frequency bands. Some of them like 28 gigahertz, 39 gigahertz, 3.5 gigahertz will require new investments. Top of that, you have the chamber, you have positioners, test antennas, probes. So a lot more systems, cost is higher. Signaling and beam management, we have to look at evaluation for beam forming, searching, tracking are big parts of functionality here. And we have to look at testing over the air by looking at mobility and beam switching. So getting details on some of this. So here is a table that shows the physical layer and compares the physical layer configurations between LTE and 5GNR. As you can see, the total number of configurations and possibilities, how you can mix basically the variable subspacing, the signal bandwidth, waveform, the MIMO operation, and carrier aggregation in 5G is just more than LTE. And this means that we need flexibility in verification of all these combinations. So this is what we were talking about earlier, the complexity of physical layer itself. To add to that, as you can see in this slide, we have the network configuration itself that adds to the complexity. So there are two ways to deploy 5G. One that we will call standalone, and the other one that is called non-standalone. So let me explain what they are. Standalone mode refers to 5G without need for a 4G core. So in a standalone mode, the core network is a 5G core, and you can see it's in green called NGC, is called next generation core. There is no dependency here on LTE core. The device can basically function only over 5G air interface, and it's called a standalone. If you come back to the other side, to the left side though, the non-standalone mode is a combination of using the 4G core, the EPC, or using the new generation core, so NGC. There is far more options here. As you can see, these are the options that 3GPP has defined so far, option 3, option 7, and option 4, depending on how the E node B, the base station in 4G, or the G node B, the base station in 5G, are communicating with each other, and to the core network, there are far more combinations to test here. So what it means for our test here is if in the days of LTE, you had an LTE UE and you would have like a LTE test system, if you take this to a standalone mode, you have a new radio, you have a 5G setup. If you are trying to test in the non-standalone, which is the major operational mode of 5G networks, then we need to be able to test across both technologies, basically. So you have to consistently operate for both LTE and for NR, and use the test cases that you have across different network options that we just talked about in the last slide. And it helps to have a common test environment across both these technologies and network options. So that is it for physical layer combinations and network options. So next thing that I would like to talk about is complexity of conformance specifications. So if you look at the technical specifications of PGPP, there is far more complexity for new radio compared to LTE. That's just the way the technology is evolving. And you can see over here, if you just look at RF, for the equivalent of LTE RF testing is many different sections in 5G RF testing. To add to the complexity of that, there is just more delays in getting the conformance specifications coming out. So that's another challenge of getting 5G out there right now. Okay, so one more area to speak about. So data speed is one of the major applications in the enhanced mobile broadband. Typically, if you compare LTE and 5G from the maximum peak data rates, LTE supports up to 1 gigabit per second. 5G will support up to 20 gigabit per second, and this is correct for both sub-6 and mmWave. So over here, I'm looking at a specific example. We picked some physical layer conditions and to come up with a typical speed for that. So you can see between bandwidth, subcarrier spacing, carrier aggregation modes, and different MIMO selections, we are achieving different throughputs between LTE and 5G. In this specific example over here, you can see throughput in LTE is around 1 gigabit per second, which is pretty much the maximum you can achieve. In 5G sub-6, we are achieving 1.7 gigabits per second, and then in mmWave 5G, we are achieving 5. And it's just using more bandwidth, it's using more number of subcarriers, and what this means for the test environment, though, it means that the test environment has to be able to replicate this high load conditions. And it's important because devices will have to be tested to evaluate both the power consumption and heat dissipation in this environment. Okay, so well, what do you do now? So given that there is all this complexity and different features to be tested, different configurations, combination of configurations to be tested, it's important that the test environment is versatile and scalable. You know, you have to test for RF and protocol, sub-6 gigahertz mmWave, and that's exactly what we have done. That's what Anritsu has done. Our radio communication test station for 5G combines all these things together, and it's based on a modular and software-defined architecture, so you can change things as you go forward. Okay, so we spoke about mmWave. We talked about the fact that a lot of the testing has to happen over the air in the OTA environment. So I wanted to talk a little bit about, well, what exactly are we? What exactly is that? How do you measure power? How do you do measurements in the OTA environment? So here's a quick summary to get it started. There are different ways of measuring power in the OTA system. One of them is called the effective isotropic radiated power, EIRP. The way this works is that we are measuring the total power radiated by a hypothetical isotropic antenna. If you have a positive dBi value, it means that we have a gain. If you have a negative dBi value, it means that it's a loss. Another way of measuring it is the total radiated power. So TRP, just to put it simply, this is sum of all the radiated power over a 3D sphere surrounding the antenna. Besides measuring power, we can also measure sensitivity. So we have EIS, which is the effective isotropic sensitivity. Again, this is measurement sensitivity in a single direction, or you can look at the total isotropic sensitivity, which means, again, we're averaging the sensitivity of an antenna or of a receiver over a 3D sphere. So now that we know what kind of different measurements we can do, the question is, what is the right distance to do that measurement? You may have heard this before, but there is a distinction between what we call near field and far field measurement. If you look at this picture, I have the UE on top on the left side, and I have two different zones, the blue zone and the red zone. each of them have two measurement points, measurement point A, measurement point B, which we call are in the near field area. And then we have two other measurement points, measurement point C and D. These are in the far field area. So what's the difference? The difference is if you're in the near field area, the measurement antenna itself will distort the measurement. That's not something that you want to do. In the far field area, basically you are far away. You're far enough from the UE. Measurement antenna is far enough from the UE that the wave is almost is seen as a plane wave from the perspective of the measurement antenna, and that's what we want. Actually, we don't want to be influenced by any of the directional characteristics of the waveform. So ideally, you want to be in measurement point C or D, and obviously measurement point C is better than measurement point D because both of them are in far field distance. Measurement point C has a better dynamic range and higher signal to noise ratio because it's closer to the UE. Okay, so we talked about different type of measurements, and then we talked about what is the right distance to do and to do measurement over the air. So why does it matter anyway? So given that we have a millimeter wave frequency range in 5G, and there is high gain antennas, they're variable phase area antennas, and they're actually needed because that's the only way to overcome the high loss that these frequencies will bring. If you just assume so you have bigger antennas now, you have more complex antennas, and the antenna size gets smaller as the frequency increases. On the other hand, you want to do the OTA measurements in the far field, so the distance will increase with frequency and decrease with the smaller antenna size. Okay, so two different ways to actually implement and measure, test this far field OTA parameter. One is called direct far field, and the other one is called an indirect far field. I am going to talk about exactly which each of them are. So, all right. So we're going to distinguish a couple different things here. Let's assume that if you look at the box on the top right, we are looking at our smartphone, at the UE. Two different dimensions here, two different, one is called D1. It is the actual size of the antenna. And the other one is D2, which is the diagonal size of the device itself. And in a little while, we'll get into why it's important. So two different methods of measurement, direct far field and indirect far field. If you look at the blue box on the left, direct far field measurements, it's very simple. We already know that we have to be far enough from the source of wave to be in far field area, and there is a formula that you can use to calculate this distance. Once you know exactly based on the frequency and the size of the antenna you're using, you can calculate R and simply put the device far enough from the source from the feed antenna, and you have achieved the far field conditions. It's great this way because the configuration is very simple, and because you can have multiple antennas transmitting towards the UE, you could actually simulate arrival of signals from different directions, which is a useful test case. The problem, though, is that when you increase the size of the antenna or the size of the device, the distance will start to increase very fast as well. So that's a problem. On the other hand, now, if you look at the indirect far field measurements, also known as compact antenna test range, we use a reflector. We use to actually create the plane wave conditions. So instead of putting the UE directly in the propagation path of the antenna, the waves are reflected off a reflector, and this actually will create the plane wave. So the advantage is that the distance needed now is much shorter. There is a different equation used. R is approximately equal to 7D, the size of the device or the antenna. But the problem is now you added complexity you need to actually account for and build a refractor, which adds to the complexity, to the cost, and to the actually makes the chamber heavier. Another problem now, because we are using a refractor, we can no longer stimulate the arrival of signals from different directions. But just to give you an idea, if you look at the same size of the device, in our example, we are looking at a 5 centimeter device, D1. The required length, the required distance in the direct far field mode is 47 centimeters. If you use a CATR chamber to implement the indirect far field measurements, the required distance is 30 centimeters. But if you look at the size D2 of 25 centimeters, the direct far field measurements will require a distance of over 1,000 centimeters, 1,175 centimeters to be exact, and which is not possible. It's not a reasonable size for a chamber. On the other hand, using a CATR chamber, you can achieve this within only 175 centimeters, which is far more reasonable. Okay, so there we have it. That's the difference between two different modes of achieving far field conditions, and there's different use cases for them that you may see at the bottom of the slide, called white box, gray box, and black box testing. That's what I'm going to be talking about next. Okay, here we have a picture and a little bit more schematic diagram of what we have in a CATR chamber. On the left side, you see the chamber itself. You see the 4G and the 5G test devices. You see the positioner to move and rotate the device inside. On the right side, you can almost look at a cut of what is inside the chamber. You can see the feed antenna, and you can see the waves getting actually reflected off the mirror inside and coming back to the quiet zone. That's where the UE, that's where the device will sit. Okay, so that's our CATR chamber, just to give you a little bit more visual of what we were talking about earlier. Okay, so as long as we're talking about different 5G and OTA measurements, I thought it would be a good idea to look at the test methodology itself as well. So we will talk about three different things here: white box testing, gray box testing, and black box testing. Very simple. If you know the actual size of the antenna in the device, and you know where it is located, you can measure, you can determine both the size that you need for the quiet zone and the far field conditions based on the actual antenna size. This is ideal if you, it's a very good use cases in R&D. You're building a device, you know where the antenna sits, you know what the size of the antenna is. If we make it a little bit more difficult on ourselves, we know the actual size of the antenna, but we don't know exactly where in the device it's located. In this case, because the antenna needs to sit in the quiet zone for testing, and because we don't know where in the device it is, we need to put the entire device in the quiet zone. So we will use D2, the diagonal size of the actual device, to determine how big of a quiet zone we need. But to actually achieve far field conditions, we can still use D1 because we know exactly what's the size of the antenna. On the far side of the spectrum, it is what we call black box testing. In this case, we do not know the size of the antenna, nor do we know where it's located in the device. So the only usable dimension that we have is the actual diagonal diameter of the device, D2. We use this both for measuring quiet zone and to establishing far field conditions. This is your typical, again, this could be used in your R&D situation, or it could be used in RF conformance testing. And because you're using the biggest dimension, this is where the CATR chambers or the indirect far field methodology comes handy. All right, so we talked about this already, just a little bit of visual of what is the DFF, the direct far field, and IFF, indirect far field measurements. I'm just going to keep our discussions to these two. There's trade-offs, of course. The DFF is the lowest cost method for in-channel measurements. Scaling of size with frequency makes the chamber way too big and too expensive for higher frequencies. So that's where the IFF method comes in, using a CATR chamber. Typically, it's more expensive, but actually it enables broadband measurements in a form factor that is possible for lab environments. All right, so that being said, let's look at a little bit of the portfolio we have over here. We basically do all of this. We do the CATR chamber for IFF. We do the DFF chamber to support multiple antennas and multiple degree of arrivals, different angle of arrivals for a beam management setup, and we have a shield box for near field testing that's we're not discussing much in this presentation. Okay, so all of that is good. Let's look at what actually is the measurement procedure for something like an EIRP. Now that we want to do this measurement, we have to get a reference value using a reference antenna, and then we put the device on the test on the positioner inside the chamber. There are two different axes of rotation to move the device around in the three-dimensional space. And each step, the positioner is rotating a device. The transmit power of UV is measured at the test antenna, and you can, based on the reference EIRP and the measured powers, you can calculate the EIRP. And then you repeat these steps 2 to 4 until we have measurements for all the points. Well, what is now important when you're looking at a three-dimensional space is how you define the measurement grid. There are 3 different kinds of measurement grids. There is the TRP measurement grid. There is the beam peak search grid, which looks for the beam, the peak of the beam, and then there is the spherical coverage grid. These are the measurement grids themselves. The grid types could be constant size stepping or constant density measurement grids. There is a little bit of visual over here. In constant step, we are literally just moving by a specific degree. in each direction. In the constant density, the goal is to achieve the same density. The stepping is not constant anymore. Okay, so here is a little bit of a summary of different grids for in-band tests. You can see the beam peg search on top left, and then we have the EIRP spherical coverage measurements, then we have the EIS spherical coverage measurements, and in the end we have the TRP measurements. We are showing the different methods supported, different implementations supported for frequency range 2. Most of them support both constant density and constant step size grids, and we have definition of what is the minimum number of points in each of these methods. For example, if you look at the TRP measurements, you can see we need at least 135 measurement points to do a constant density measurement. If we are looking at constant step size grid, there's 2 different ways to implement it. Each of them require 192 minimum measure points. So a question that typically comes up is, why does it matter if the number of the minimum number of points is larger or smaller? The answer is the measurement time. So let's take one example here and look at the measurement time of the TRP total radiated power parameter. So the total measurement time is affected directly by the number of measurement points. Very simply put, the total measurement time is equal to the time it takes to move the positioner plus the time it takes to actually do the measurement, multiplied by the number of the points, multiplied by 2, and 2 is to account for both type of polarization, horizontal and vertical. So in this table we have here, you can look at different number of measurement points, and then look at the measurement time per point, 3 different measurement times, and we are actually providing the total measurement time. You can see as the number of measurement points increase, the total test time increases significantly. All right, so that being said, similar challenge when you look at measurement time for spurious emissions. By the nature of spurious emission measurements take a longer time. So in this specific example, which I will not get into, but basically we are choosing and fixing the specific bandwidths and parameters we are looking at measurements per bandwidth. We are assuming that the time it takes to do the measurement is 10 milliseconds, and number of averages is 1, test grid degrees, and total points to get to a whole sphere is only 266 points. If you sum this up, it takes over 60 hours to do this test case. A big problem, as you can see, test time is increasing very, very quickly. So there are efforts to reduce the time it takes to do measurements. One of the easiest ways to look at it is, let's just take TRP measurements. Instead of stopping the positioner for each measurement, you can design the system so that you measure without stopping the positioner by a trigger. Obviously, you will need a continuous signal. In a non-signaling mode, you can do this, and it will save some time. In this specific example that we were looking at, total test time will go from 15 minutes to 6 plus 4, 10 minutes. All right, so a quick look at different type of measurements and what you will gain actually after you do all this configurations and go through all this over-the-air measurements. You can look at the top left. You can see transmit power, occupied bandwidth, SEM, ACLR, frequency error. On the top right, you can see parameters such as EVM, phase error, magnitude error, and constellation. And you can even see a 3D graph of the, I believe this is a TRP measurement in 3 dimensions. So this was the goal, correct? You go through all the steps and different methods of measurements so that you have these parameters over here. A quick summary of supported RF measurements. You can see for the different test items, such as transmitter maximum output power, or the EIRP, the NPR, ANPR, configure transmit power, minimum output power. Over here, you can see what is available in the conducted measurements. Some of these measurements, by definition, are only for mmWave, such as, like over here, you can see transmit power is supported both in conducted and in form of EIRP or TRP measurements in mmWave. Okay, so on top of this, we support beam peak search, which is very important for the functional testing, and a combination over here of different number of carrier aggregations and MIMO configurations. One thing to note here is that there is 2 implementations in frame structure, FDD and TDD, for frequency range 1, and in frequency range 2, there is only TDD frame structure to this date. Okay, so we talked about the measurements. Now let's take a go back to the portfolio. CATR chamber we talked about. The anechoic chamber, the middle, the direct far-field chamber is the next topic I will cover. But before I get there, let's talk about measurement uncertainty and test tolerance. 2 very important concepts for a test system. Starting with measurement uncertainty, because we are looking at uncertain measurements in or attributes to a measured quantity, we have to collect in statistical value. So each factor that is uncertain in the measurements will be we'll have to collect it in a statistical method, get the standard deviation for that factor, get the root sum square, and use this expanded measurements with 95% probability. That's the definition what is measurement uncertainty. And test tolerance is simply what the standard, what the regulation is defining to the minimum requirement. So the passable criteria will be your minimum requirement plus the test tolerance. Okay, so because we have gone over the air, we have added extra factors to the measurements uncertainty, MU. So now we went from a cable to transmission over the air. So the SNR is decreasing, the free space path loss is increased, is added to our factors. The quality of the quiet zone itself is something that needs to be validated. It adds to the MU. The absolute gain of the calibration antenna is another thing to be added. Because the frequencies have increased and we are over 6 gigahertz now, for the OTA measurements, the impedance mismatch also will increase the measurement error. So typically, if for similar conditions, for comparable conditions, if you have around 1 dB of measurement uncertainty for a system, same system in frequency range 2 will have something close to 5 dB. It's a big performance impact for 5G service. Beam peak search, one of the other topics we were looking at. So there is a need to find out the maximum output or sensitivity direction of the user equipment. And we have to do a 3D scan around the UE to find this direction. Here's an example of UE with different beam directivity and different size and magnitudes and beam width in different directions in the three-dimensional space. Process of beam management is very important for 5G. Basically, it's needed for stable mobility operation. To put it simply, the UE selects the best beam conditions and starts its access process to the G node B. Once it has done that, it will report the detailed information of beam back to the G node B, and the G node B will assign the best beam for that UE. Once this has been completed, the UE will simply adjust the direction of the uplink signal and based on the downlink beam. That's to put it very simple. How is this tested? Fortunately, the direct far field setup that we have will support this. You can, very simple example over here. You can see there is a 5G G node B simulator. It's simulating two different G node Bs and putting them through two different feed antennas to the OTA chamber. So in this case, you can simulate two different beams and control their direction to device under test. Okay, so I'm going to wrap up and get into kind of like a conclusion of what we talked about so far. As you can see, there is different stages of testing from that Anritsu participates in, from design, from R&D and design of the chipsets to commercial UE R&D to conformance testing to carrier acceptance testing, and all the way to manufacturing. We are very much involved in and contribute to the 5G development. We work with Qualcomm, with Apple, MediaTek. We have done standalone, the first standalone integration with Qualcomm. We also work with a lot of other vendors for over the air and for regulatory testing such as SAR testing, and we work closely to add to the 5G certifications. We work with one of our partners, ETS, and a couple other industry leaders to get validation in GCF, in PTCRB. That being said, I'd like to hand this over back to Bill to see if you have any questions to answer.
Thank you. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, please type your question into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. So for our first question, how do you compare the rollout of mmWave with sub-6 gigahertz frequencies?
Okay, great question. Specifically speaking, the rollout of the mmWave is what we have seen at least happen a little bit in the US is to support mostly higher bandwidth. So frequency range 2 deployments typically have a smaller coverage, like stadiums or dense urban areas are good examples. They are typically running in conjunction with 4G or as a small cell. They provide this additional, basically they provide the additional bandwidth. For sub 6 gigahertz, it's the opposite. The coverage is better. You can have far better coverage and mobility applications between LTE and 5G. But because the bandwidth is, the bands themselves are less available, the total available bandwidth is smaller. You can't get to the higher carrier counts that you could do in millimeter wave.
All right. Next question is, what needs to happen to fully unleash the potential of 5G?
Okay, great question again. As we were talking about this earlier in the presentation, there is many things that needs to happen. First of them is we have to wait and see, wait for the 3GPP and the standards to complete. Again, what we have today is the core functionalities out there just to get things started. A lot of the enhancements, a lot of specific applications we talked about, like URLLC, like MMTC, they will not be available, or at least they won't be optimized and enhanced until release 16 and release 17 are out the door. There will be a lot more of devices coming to the market that enable these applications. Also, LTE probably is going to stick around for a while, and step by step as the investments come in and the technology matures, 5G will be, we will see more and more of a standalone 5G network operating.
Okay, well, we're going to have to wrap up now, and we'll have to get back to those other questions via email. Before we leave today, I'd like to remind all of you that by registering for today's event, you have full access to the 5G Bootcamp Content Gateway. This site contains a host of resources that will equip you with vital information. We have made finding the right content for you easy. You can simply select from our categories, and all with a simple click of a mouse button. On behalf of Electronic Design, I'd like to thank Anritsu for sponsoring today's event, and of course to all of you for joining us. Have a great rest of the day.